All right, next I'd like to look at different versions of the torque equation. So far we've looked at the one in which we have a force applied, let's say in this case to a beam, that comes out such that the angle theta between the radius vector r and the force F is given, and that expression for the torque is F sine theta times r. Okay, so that's what we've looked at so far, but there is also an equivalent formulation that uses what's called the lever arm. And the lever arm is what is often referred to as r perpendicular. And this turns out to be equivalent. And sometimes it's more convenient to use the r perpendicular F formulation, which we're going to look at. Some examples of where that's true pretty soon. And so if we want to write it this way, then what we do, and these are the steps for getting r perpendicular. One is we just extend the force vector line. Step two, we draw a line from our pivot point, which is here, to the point, along the path of minimum distance to the force vector line. So this path of minimum distance from the pivot point to the force vector line is going to be perpendicular. And it's the path of minimum distance, both. Okay, and so you just drop a perpendicular then, in other words, onto the force vector line. And that becomes your r perpendicular. Now how does that relate? It should give us the same result as we got here. But r perpendicular, if this is r, and because vertical angles are equal, this is still theta, then r perpendicular is r sine theta. Okay, so we can rewrite the torque then as r sine theta, which is r perpendicular, times F. But we see that that's exactly the same as writing it as F perpendicular times r, because in both cases it's just Fr times the sine of theta. But in some cases, this application of the torque equation is easier to implement. And so I'd like to take a look at an example where we could use that. In this example, we have a climber. And let's say that this climber has really good hiking shoes, and she is attached to a rope that goes up to the cliff face here. This is the cliff face, this is a rope, and that rope goes to her center of mass position. Okay. And associated then with the rope pulling up on her center of mass position, she is suspended here. And what we want to ask is, at what is the maximum coefficient of static friction between her feet and the cliff face that will allow her to remain suspended if this angle here is 60 degrees. should say this is the coefficient of static friction minimum, because if you had something that was larger than that, that would also hold her onto the cliff. Okay, so her feet then are attached to the wall here, and so we must have a static friction force acting from this position as well as a normal force. So this will be F normal of the cliff face, or the wall we could call it. And because she's going to tend to slide this way, we're going to have a force static maximum. Okay, so we're going to push the static friction force to the breaking point by saying what is the minimum coefficient of static friction that will hold her to the wall. Now, I've seen a lot of solutions to this problem that take pages and pages of calculations. And this is actually done by people that are supposedly know what they're doing that are writing these textbooks. But this turns out to be a very simple problem if we use the right pivot point. Okay, now, we're not really told here exactly how far her center of mass is away from the cliff face. And we're not really even told what the mass is of her body. And yet, we know that this angle is 60 degrees, and we know that these two forces are going to act. And we don't know what this angle is for the rope. We know that this angle is 60 degrees. So we have a tension force that's acting here. We have mg that's acting here. But it seems like we don't quite have enough information to solve the problem. However, if we choose her center of mass here, and remember that's where the tension force is pulling from, and we'll also assume that her weight force is also acting right through the center of mass position. Then by choosing this as the pivot point, we can measure everything with respect to that point, and we can eliminate the unknown weight and also the unknown tension. Okay? And then the static friction force is going to be related to the normal force. So we actually do, although it doesn't seem like it here, we actually do have enough information to solve this problem if we choose this as our pivot point. Okay, so how do we proceed? Well, once we know that that's the pivot point, then let's, even though we don't know what this length is, let's call it L. Okay, so that's the distance then from where her feet are in contact with the cliff face to the position of her center of mass. And let me just draw that part of the triangle a little bigger here. So we have F normal wall, we have F static maximum, and we have her at a 60-degree angle, supported from this position a distance L away from her feet to her center of mass position. Okay, so L then is the distance to the center of mass from point of support on the cliff. Okay, so this, remember, is our pivot point here. So we have tension going that way, mg going that way, but those are intersecting with our pivot point, and so therefore that is not part of the torque equation. And so what we can do here then is we can say, okay, well, about this pivot point, we can do an R perpendicular F calculation. And so let's do that first for F static maximum, and then for F normal wall. So what we want to ask ourselves then is, what direction does F static max make the system want to go? So that turns out to be a clockwise direction. So we'll write this as F static maximum times, and then how do we get R perpendicular? Well, R perpendicular, we're just extending the static friction force vector until we can intersect that from the pivot point with an R perpendicular, which intersects the force vector line at a 90-degree angle. So this is R perpendicular to F. Okay, so R perpendicular then is going to be equal to L times the sine of 60. Okay, so we have F static max times R perpendicular, which is going to be L sine 60. Now similarly for the F normal wall, we can extend that force vector line. We can draw a line that goes from the pivot point such that it intersects the force vector line at a 90-degree angle. And so this is going to be our other R perpendicular, 2, call this R perpendicular 1. So R perpendicular 2 associated with the F normal wall. And so if this angle here is 60, then that makes this angle here 60, so that becomes L cosine 60. So we can write that in here then as F normal wall times L cosine 60, like that. Okay, so it looks like maybe we're in a little bit of trouble here, but not really, because now we just set the clockwise torque equal to the counterclockwise torque. That gives us F static maximum times L sine 60 equals F normal wall times L cosine 60. Now remember that we were looking for the minimum value for the coefficient of static friction that will allow her to not slip as she is doing her mountain climbing. And so the L's are going to cancel, and F static max we can write as mu s times F normal wall times the sine of 60 equals F normal wall times the cosine of 60. Or we can cancel out the F normal walls, and we can say that mu s is equal to the cotangent of 60 degrees, cosine over sine. And so that's it. That's the solution. It's equal to the cotangent of 60. So what in the world is the cotangent of 60? Well, let's draw our 30, 60, 90 right triangle. This is 1, 2, root 3. Tangent of 60 would be square root of 3 over 1, opposite over adjacent. So the cotangent would just be the reciprocal of that, so that would be 1 over root 3. And so that's our solution. Cotangent is equal to 1 divided by 1.73. Which is 0.57. And that's it. However, if we had to try to figure out what all of these other angles were, and we used to say this is our pivot point, then we'd have pages of calculations. It's still possible to solve it, but it could take days. And so this is our preferred solution for this problem.